Hi everyone, I am Chunyang Wang from Nanjing University. Today I will talk about towards derandomizing Markov chain Monte Carlo. It is a joint work with Wei Ming, Hen, Jiahen, and Yitong. A central question in the theory of computing is to understand the power of randomness. One early and surprising illustration of its power is through estimating the volume of a convex body. It has been shown that deterministic algorithms cannot achieve good approximation ratios through membership queries. Yet Dyer, Fries, and Cannon discovered an efficient randomized approximation algorithm under the same model. The driving force is the celebrated Markov chain Monte Carlo method. By applying the reduction by Germ, Valiant, and Verrizani, one often reduces a counting problem to a sequence of related sampling problems, and the latter is solved using Markov chains. This powerful method has led to many great achievements, ranging from the early results of approximating the partition function of ferromagnetic Ising models and the permanent of non-negative matrices, to more recent developments such as counting the number of bases in matroids and estimating partition functions of spin systems up to critical thresholds. While randomness remains an indispensable ingredient to the MCMC method, the belief that randomness is essential to efficient approximate counting is seriously challenged over the past 2 decades. Starting from White's decay of correlation method, which gives an F-pitas for sharp p-hard problem, deterministic algorithms are gradually catching up with their random counterparts on many fronts. This includes decay of correlation method, zero freeness of polynomial method, linear programming method for constraint satisfaction problems, and many other statistical physics-related methods, such as the cluster expansion method. Curiously, although these algorithms are usually guided by probabilistic intuitions related to the problem, they work very differently from typical randomized algorithms. All these developments beg one question: can we de-randomize MCMC more directly? The benefit of a positive answer would be twofold. It can help us better understand the role of randomizations in MCMC and in approximate counting. It might also lead to easier ways of designing deterministic counting algorithms, thanks to the plentifulness of MCMC algorithms. We consider a class of generic Markov chains known as single-site global dynamics, also known as shape sampling or heat bus dynamics. We assume the state space is the assignment of one of the Q spins to each variable. In classical MCMC, a Markov chain is simulated chronologically for a long enough time to draw a sample according to the desired stationary distribution mu over all possible states. Here, we start from any feasible configuration, each time randomly choosing a variable and updating its value by drawing from the marginal distribution, conditioning on the current state of all other variables. We first consider the problem of sampling from the hardcore model. Here, given as input a graph G and a fugacity parameter lambda, we are asked to sample from the distribution over independent sets of G, where each independent set has weight proportional to lambda to the size of the independent set. For hardcore model, the transition rule of the global dynamics becomes simpler. Here, to draw from the marginal distribution, we look at the neighbors of the current vertex. If there's already some vertex in the independent set, or occupied, we force the current vertex to be unoccupied. Otherwise, we let the current vertex to be occupied with probability lambda over 1 plus lambda. We can simulate the update step by drawing a uniform random real at each time in advance, and perform the update according to the value of the random real. This gives explicit randomness for updates. Here, in single-site global dynamics, we have another source of randomness, which is the choice of variable at each time. For better illustration, we first show how to deal with the randomness during the updates by considering a variant that is called systematic scan global dynamics, where the vertices are chosen in any predetermined cyclic order and the update rules remain the same. So for example, we initialize the states of all vertices as all unoccupied, which is surely feasible. At time t equals to 0, the vertex we are going to update is v0. It has no occupied neighbors, so we need to look at the random real r0. It says it's greater than or equal to 1 over 1 plus lambda, so we update it to occupied. At time t equals to 1, the vertex we are going to update is v1. It has an occupied neighbor v0, so we update it to occupied no matter what R1 is. And similarly, we can perform the update at t equals to 2 and t equals to 3. It can be shown that when the chain is irreducible, it converges to the desired distribution as t tends to infinity. In practice, we analyze the mixing time of such Markov chains and run up to properly long times to get a sample with bounded bias. A classical result by Hayes and Sinclair showed that omega n log n steps are needed for such systematic scan global dynamics to produce a sample with constant bias. Challenges arise from this classical result, as trivial derandomization by brute force enumeration will then take exponential amount of time. Short of a breakthrough in pseudo-random number generators, it seems impossible to fully derandomize Markov chains. Here is the saving grace. The Monte Carlo step of MCMC does not require fully simulating the Markov chains anyways. Looking at the update rule of the systematic global dynamics for the hardcore model, you can notice that if the random real RT is less than 1 over 1 plus lambda, then the state of V can already be determined without even looking at the state of its neighbors. Recall that for approximate counting, usually only the marginal probability of a single variable needs to be evaluated rather than the whole state, and this can be done by taking the final state of some vertex after the global dynamics. When lambda is relatively small, this single observation gives us a decent amount of probability of determining the final state of some variable by only looking at the random real at its last update time. Here in the following table gives the predetermined update sequence for each time, and here all random reals RT and the results are initially unknown. We assume our Markov chain runs from time minus t plus 1 to 0, instead of 0 to t minus 1. Without loss of generality, say we want to know the final state of vertex v5. A feasible method is to simulate a systematic scan global dynamics up to some time and take the final value of vertex v5 as a sample. We can look at the randomness at time 0 first. If R0 is less than 1 over 1 plus lambda, we already know its state is unoccupied in the final state of the Markov chain without knowing all other RT. Suppose the opposite, that R0 is greater than or equal to 1 over 1 plus lambda. We need to know its neighboring vertices state at that time to decide its final result, which get last updated at time minus 3 and minus 1. We then find their corresponding RT respectively. Suppose at time t equals to minus 1, RT is less than 1 over 1 plus lambda, and at time t equals to minus 3, RT is greater than or equal to 1 over 1 plus lambda. Then we already know the state of V4 at time minus 1, but don't know the state of V2 at time minus 3. To learn its state, we need to further know the states of its neighbors at time minus 3, which get updated at times minus 6, minus 5, and minus 4, respectively. Suppose all RT at these times is less than 1 over 1 plus lambda, then we know their respective states are unoccupied. Hence, we know the state of V2 at time minus 3 is updated to occupied, and the state of V5 at time 0 is updated to unoccupied. Our process then finishes. We can conclude the process above as a subroutine resolve sub big T small t to denote a procedure that returns the outcome of V t mod n at the time t of a big T step global dynamics. The procedure first checks if t is less than or equal to minus big T or not. If it does, we simply return according to the all unoccupied initial state, which gives unoccupied. Otherwise, we visit the random real RT at the time. Here we note that this RT is stored in a map, only sampled at first visit, and hence the value it returns is consistent for multiple queries with the same T. If RT is smaller than 1 over 1 plus lambda, we can simply return unoccupied. Otherwise, we need its neighbor states to determine, where we only need to apply recursive calls of the same subroutine resolve. Here, in systematic scan global dynamics, we can directly know the last update times of each vertex before time t. If any of them returns occupied, we return unoccupied, and return occupied otherwise. This provides us an approximate marginal sampler that always terminates, as we sample each RT at most once, and there are at most big T times we can visit. Note that this idea is not restricted to the hardcore model. and can be applied to a wide range of problems where the marginal of each vertex has a lower bound, no matter what its neighbors has. We call this generic algorithm coupling towards the past, or simply CTTP, as it resolves the state of a vertex in reverse chronological order. And there is in fact a hidden grand coupling in the algorithm that for each possible configuration, the same set of RT is used. In fact, this coupling towards the past technique can also be applied assuming the chain runs from infinite past to time zero. Then the distribution of the configuration at time zero is exactly the desired distribution. Here our subroutine becomes even simpler, as it doesn't need to check if the current time is smaller than or equal to minus big T or not, and this provides us a perfect marginal sampler, assuming it terminates. We can see that here each subroutine directly returns with probability 1 over 1 plus lambda, and incurs at most delta recursive calls otherwise, where delta is the maximum degree of the graph. Hence, the subroutine terminates with probability 1, when lambda is less than or equal to 1 over delta minus 1. In classical applications under certain regimes, we can show that the probability that the number of timestamps visited exceeds some threshold big T is exponentially small. So truncating the process after some logarithmic threshold already gives us an approximate sample with small enough bias. We can then apply the trivial enumeration method to derandomize this process, leading to a running time polynomial in N. From a complexity theory point of view, our construction of marginal samplers from the original Markov chain algorithm has a certain direct sum flavor. We transform a protocol for sampling n variables to a new protocol for sampling single variables, using only 1 over n fraction of the original cost each. The core of our derandomization method is a logarithmic cost marginal sampler, which may have independent interests. Our main source of inspiration, and also the first such marginal sampler, is the recent recursive algorithm by Anand and Jerome for perfect sampling in infinite spin systems. The two algorithms share several similarities, such as giving marginal samplers with logarithmic number of random bits, and both relying on the marginal lower bound distributions. A major distinction is that our algorithm comes from a different source of MCMC. Another is that AG algorithm encounters some difficulty in matching the state-of-the-art bound for some randomized algorithms. Our marginal sampler is also inspired by the celebrated coupling from the past, or CFTP, by Prop and Wilson for perfect simulation of Markov chains. However, they are also very different in several aspects. The main difference is that CFTP needs to sequentially simulate the evolution of the whole state, which, even with some optimization, such as using bounding chains and under favorable conditions, would still require at least linear time. This makes it unsuitable for our derandomization needs. We then show some applications of our CTTP method. The first is for approximately counting the number of hypergraph-independent sets. Given a k-uniform hypergraph as input, a subset of vertices is said to be independent if no hyperedge is fully occupied. For this problem, the work of Herman, Sly, and Zhang shows that the standard global dynamics has an optimal O and log n mixing time when delta is less than 2 to the k over 2 times some constant. A later work by Chunyang Wang and Zhang further developed a perfect sampler based on the technique of coupling from the past under a slightly worse regime. All these results are nearly optimal due to a lower bound by Bedakova, Jelenis, Goodberg, Guo, and Stepankovic. However, for this problem, the regime for deterministic counting is lagging behind. The state-of-the-art before this work is delta less than 2 to the k over 5 by He, Wang, and Ying, leaving an exponential gap, where this tilted inequality hides lower-ordered factors such as k. In our work, we applied the CTTP technique to this problem, achieving a bound matching the previously mentioned randomized algorithm and hardness threshold up to a factor of OK squared. Applying CTTP for a hypergraph independent set, or simply HIS, seems quite straightforward. The global dynamics for HIS is at most almost the same of the global dynamics on hardcore model when lambda equals to 1. Here, each vertex has a 1 over 2 lower bound for unoccupied. When failing to determine the state of a vertex using the lower bound, we need to resolve the state of its neighborhood, which include k-delta vertices. We need to notice that if we apply the same strategy we used before, we need the regimes to become k-delta less than 2, even for the CTTP to terminate, which is clearly not possible. Here, we equip a more clever strategy that first checks the random rail sampled on all neighboring vertices, and recurs for all vertices on a hyperedge only if all random rail on them are greater than or equal to 1/2. I will sketch the analysis for this more clever strategy shortly after. Another application we consider is counting the number of proper hypergraph Q colorings. Given a K-uniform hypergraph, a Q coloring of its vertices is proper if no hyperedge is monochromatic. For this problem, the randomized state-of-the-art is by Jian, Fan, and Wang, and He, Sun, Wu, achieving a delta less than Q to the K/3 regime by the method of compression and MCMC, which we will then briefly introduce. The state-of-the-art for deterministic counting before this work is delta less than Q to the K/5, still by He, Wang, and Ying, leaving an exponential gap with the randomized algorithms. For this problem, the current lower bound is Q to the K/2 by Galanis, Guo, and Wang. In our work, we apply the CTTP technique to this problem, also achieving a bound matching the state-of-the-art randomized algorithm, and closed the gap between deterministic and randomized algorithms. For the problem of hypergraph colorings, the natural global dynamics is unfortunately not irreducible. Hence, we need the idea of compression by Feng Guo Ying Zhang and Feng He Ying. Here, by compression, we mean dividing the Q colors into buckets of some smaller sizes. We run MCMC to decide which bucket each vertex is assigned to, and finally decide the color of each vertex, conditioning on their respective buckets using the rejection sampling method. This compression improves connectivity and helps make the MCMC become irreducible. For this problem, we do not have any natural lower bound for each vertex. However, a lower bound is still guaranteed when the bucket sizes are large enough, using the celebrated Lavash-Local lemma. The complications of hypergraph coloring is that after compression, our desired distribution of buckets is no longer a gypsy distribution, meaning we cannot only look at the neighboring vertices when determining the state of a vertex. However, it suffices to only look at the states of the vertices in the same connected component, after removing all hyperedges that can never become monochromatic, conditioning on the current bucketing. In our algorithm, we need to find this connected component on the fly in a breadth-first search manner, while also equipping the same more clever way of recursing as in hypergraph independent sets. For the analysis of both hypergraph independent set and hypergraph colorings, the only thing we need to show is that the random bits our algorithm used decays exponentially. This implies that the truncation error is small when we set a logarithmic truncation threshold. For this, we need to analyze on the so-called time-space hypergraph, which was an infinite graph or hypergraph formed by unrolling the dependencies of each time. Here, the graphical illustration is for the hardcore model, and we have more complicated hypergraphs for the problem of hypergraph independent sets and hypergraph colorings. Then for the analysis of the number of bits used, we apply a simple witness argument showing that if a large amount of random rails have been visited by CTTP, then some witnesses with very low probability occurs, then this is enough to take a unibound of all possible witnesses. In the case of hardcore model, this bad event is simply that all the random rail at the visited times is greater than or equal to 1/1 plus lambda. Yet, we almost finished the techniques and applications of CTTP on systematic scan global dynamics. However, in theoretical computer science, much more analysis is focused on random scan global dynamics than systematic ones. Despite introducing more randomness, is it possible to still use CTTP and de-randomize random scan global dynamics? Our first try would be to enumerate all possible visited scan sequences in the correct order, which would take super polynomial time and is not feasible. Our solution is to notice that we do not need the total ordering of all vertices to deduce the outcome of our CTTP. All we need is the information of a locally total ordering, which can be captured by the construction of a certain kind of witness trees that starts with the last vertex in the scan sequence goes backward in time, each time append to neighbor with the largest steps, breaking ties by lexicographical order. As an example, say we still have the hardcore model, and this is our graph, and this is our witness scan sequence. We can then construct our witness tree as follows. So it looks like this, and we have our witness tree. So, so each vertex has is finished our construction of the witness tree. So each vertex has both delta sums in witness tree, where we recall that delta is the maximum degree of the original graph. The amazing fact is we can deduce the outcome of CTTP by only looking at this witness tree instead of the original sequence, as this tree already tells us a local total order. That is, for each pair of visited adjacent vertices in the scan sequence, we can tell their relative chronological order by comparing the depths of vertices with their labels on the witness tree. For example, for a pair of neighboring vertices v4 and v5, we can know the relative chronological order of all visits at these two vertices by looking at the depths of the vertices in the tree with their labels. The same holds for v2 and v5. What's more, there are only poly delta k q delta to the k q to the k possible witness trees, meaning the number of possible witness trees is polynomial in n when k is logarithmic. We can also apply dynamic programming to solve the probability of occurrence for each witness. Then a brute force enumeration would successfully de-randomize a random scan global dynamics. We mentioned that this construction of witness trees almost coincides with the witness trees in the analysis of Moser-Tadish algorithm for the algorithmic low-local lemma, which may be of independent interest. We summarize our work as follows. We propose a new framework, CTTP, which gives lightweight samplers that can draw from marginal distributions for de-randomizing MCMC algorithms. As concrete applications, we obtain efficient deterministic approximate counting algorithms for hypergraph independent sets and hypergraph colorings in regimes matching the state-of-the-art achieved by randomized counting sampling algorithms. For future directions, our CTP relies heavily on the marginal lower bound, which is a consequence of the grand coupling. This heavily restricts the problem we can study. For example, for graph colorings, no such lower bound holds, and yet efficient deterministic algorithms exist. It would be very interesting to find alternative ways to implement CTP without marginal lower bounds, to match the bounds from other methods. Another direction is that our CTTP effectively decomposes an O and log n step Markov chain to an O log n step marginal sampler, whose random choices are enumerable in polynomial time. It is then a challenge to de-randomize those MCMC algorithms with significantly higher mixing time bounds to have. For example, local samplers, marginal samplers for graph matchings or bipartite perfect matchings. The last one, and possibly the hardest. Currently, all non-deterministic approximate counting algorithms, including ours, suffer from running time bounds whose exponents depend on the parameters of the problem or the instance, when the instance is close enough to the critical threshold. It is still wide open to give a deterministic approximate counting algorithm with a truly polynomial running time under such circumstances. That's the end of the talk, and thank you.